kind of wrapping up chapter 3. As I told you on Friday, we are going to do a little bit of chapter 4. We really need to get into that because your lab next week is going to involve a lot of chapter 4. So I want to make sure that we've covered that by the time you get to that. So I do want to go through one thing that I didn't have time for on Friday. I think this was the class. Did we talk about my diagram in the back there on Friday? Okay. Well, then I guess I don't need to go through it. One thing that I did want to point out, we talked about using it just to go between two related things. But our last problem that we did when we were finding the mass of potassium iodide, we were up here is what we wanted to get, and the information we had down here. So this can kind of tell you what to do. Okay, I'm not going through density. I don't know the density, so I have to go all the way around, which means I have to go those first and then get the mass. So if you have the thing you want and the thing that you have are very far apart, this can kind of tell you the steps to take to get there. So there is that. All right. So I want to look at types of reactions. And this is what is in chapter 4. Oh, and the prepare to learn for chapter 4, the beginning of the chapter is going to be due on Tuesday. And if you haven't finished the vocabulary, you're going to want to do that as well. Okay. So there are lots of ways to organize types of reactions, and we don't always organize them the same way, and we definitely don't cover every type of reaction. So this is just common reactions. So basically, there are two sort of methods we can use to break down our types of reactions. One of them is counting our reactants and products. And this makes some of them pretty easy. And then method 2 is looking at what types of chemicals we have. And your lab kind of mushes both of these methods together. There are some things that fit into categories in both of these, and there are some of them that only fit into categories on one and not really into a category on another. So that's why I'm going to look at both of them. So with method 1, we have basically 3 options. Either we are combining things, we're breaking one thing apart, or we're switching places. So we want to know how many reactants and how many products. So if we start with something that is a synthesis, this is where we are combining things to make one thing. So we will have 2 or more, so I'm going to put 2 plus reactants, usually just 2 in our reactions, but you could theoretically have more. So you bring 2 things together and you only have 1 product. So you can always identify that because there's only 1 product. So the reason I do this one first is this one's a little bit simpler to identify than the others. You don't really have to think about what the chemicals are, you just have to count. The reverse of this is a decomposition. And so in a decomposition, we start with one reactant and we end up with multiple products. All right, so let me do an example. There are many metals that if you heat them or burn them in oxygen, they're going to combine with the oxygen. So we might have iron and oxygen and form basically rust. Okay, so two reactants, one product. All right. We have decomposition that can occur in a couple of ways. So one is when we have something like our hydrated ionic compounds where we're just driving off the water. So that doesn't really change the rest of the chemical composition. So in lab, you had magnesium sulfate, and I think that was heptahydrate. So this is all one compound. There's no plus in there. And then we ended up with our products being magnesium sulfate plus 7-1. So 2 or more products. Okay, so those two are pretty easy to identify just by counting how many things are there. Now we can also have decomposition reactions that are going to change where the electrons are. And we'll talk more about this later. In this case, the charge on the magnesium is 2+ here, and the charge on the magnesium is 2+ here. But if I had something like mercury oxide, HgO, oxygen's a 2-, so here the mercury is a 2+, but I can decompose that, make mercury. Now, mercury is unusual as a metal because what is it like at room temperature? Liquid. So it is one of 2 elements that can be found as a liquid at room temperature, and then oxygen is a gas. Okay, so one reactant, multiple products. Okay, so on another day, we will talk about where the electrons are going and how we identify those things. Okay, so that's kind of the main ones that we typically look at by counting. Yes?
Why did nothing change on the second one?
What do you mean, why did nothing change?
When the reactants were added, so it looks the same.
Well, we have only one oxygen here, and here we have 2. Here, this is an ionic compound. Oops. Okay, so they're all wedged in together like this. Here, we have the mercury atoms that are just kind of fluidly moving around each other, and then we have oxygen molecules. Okay, so it will look different. This is a red compound. It's a solid kind of powdery, and then this is a silvery liquid, and then the gas, of course, we can't see. So they are different, even though the elements are the same. Yeah. Okay. So with double displacement, we're going to have 2 reactants and 2 products. And here we have to pay a little bit of attention to what kind of thing they are. Are they a compound or are they an element? So in double displacement, they are both compounds. usually ionic. And so what we do with a double displacement reaction is, since we have ionic things, we're going to change who the partners are. So the positive ions are going to switch which negative ion they're attached to. So, so if I take something like AgNO3, Ag is silver. What is NO3? Nitrate. And react that with NaCl, sodium chloride. Now these would generally be in aqueous solution. So I'm going to put AQ by this. I could get a reaction if I just dumped the salts together, but it would take a very, very long time. So if I put them in water, this happens very, very quickly. So when they react, they're going to form AgCl. So silver is positive, and it's going to switch the negative thing that it's attached to from the nitrate to the chloride. Now, why won't the silver get together with the sodium? They're both positive. So those two positive things are going to repel one another. So if it's going to switch partners, it has to grab onto the other negative thing. Then sodium, which is positive, is going to get together with the negative nitrate. NaOH. All right, so these are simply switching partners. This is sometimes called metathesis. And you'll see that name from time to time, especially among people who want to sound like, yes, I'm very intelligent. I know the word metathesis. But it's usually easiest to think of it as just a double displacement. I'm changing two things. Two things are switching partners. Okay. What typically happens in this type of a reaction is that when they switch partners, one of them is insoluble. And so we'll look at solubility rules later. So it turns out that silver chloride will not dissolve in water. So when those get together, they're going to form an ionic compound. But sodium nitrate is going to stay aqueous. Okay. Okay, now the thing is that when they switch partners, they still have to charge balance, which means that if I have a +2 with a -1, I need to make sure that I get two of those -1s together. So let's say that I have calcium chloride. So what's the charge on calcium? +2, because it's in the second column. And chlorine's a -1, so I need two of those. Okay. Now, if I react that with, let's do sodium, sodium sulfate. Now, sulfate has what charge? -2, and sodium is +1. So I need two sodiums. I put my little 2 in there. Then the products are going to have to rearrange so that the charge is balanced. So part of the benefit of being able to identify what kind of reaction you're looking at is to be able to predict what the products are going to be. So if we were to predict this, we need to make sure that our calcium goes with a different anion. So what is the anion it's going to match up with? The sulfate. And we said this was a -2 and calcium was a +2. So if there's one of each of them, do they cancel? Yeah, right? The +2 cancels the -2. And then the sodium is going to get together with which ion? The chloride. Okay, and remember, because sodium is positive, the only thing that it can get together with is the negative ion. So that's why it has to go with the chloride. We said sodium is a +1 because it's in group 1. Chloride is a -1 because column 17 is always -1. So do I need to add any subscripts here? No, so it's good. However, one of the things we got to do on our quiz today is balance. Is this balanced? Not yet, because I got 2 chlorines over here and only 1 over there, similar with the sodium. So what would I do to balance this?
Put it to sodium chloride.
All right. So take a second to look at that. Does that make everything balanced? Seeing a few nods. Yes, it does. Because it gives me the 2 sodiums, gives me the 2 chlorines, and then I only had 1 each of the calcium and the sulfate. Okay. Okay, so that's an example of a double displacement. There is another kind of double displacement that you can think of it like an ionic reaction, but one of the products is actually covalent, and that is an acid-base neutralization. So let's say I had HCl. That's what acid? Hydrochloric. So we use hydro because there's no oxygen. If there were an oxygen there, then we would not say hydro. This is hydrochloric acid. And we're going to react it with the ionic compound NaOH, which goes by the name sodium hydroxide. And these are going to react. So let's look at the sodium first. Sodium is a +1. Which is it going to get together with, the hydrogen or the chlorine? The chlorine, because the chlorine is the negative one. And then we had talked about hydrogen when it's an acid, it acts like a +1, right? Because it changes the charge of carbonate from a -2 to a -1 when it becomes hydrogen carbonate. So this is going to be a +1. So we'll get together sodium and chlorine. So we got an ionic compound there, but what's left over is this hydrogen and this OH. And when I combine those, I get H2O. Okay, so it really works the same way, but one of our products here is water, which is not ionic. So that's the only difference in how we would predict the results. If you recognize that you're looking at an acid and a hydroxide, then you can know right away, water is one of my products. So let me write down water and figure out what else is going to go into making the other remaining product. Okay, so this is how we would break it down by reactants and products. Oh, there's one more I wanted to look at. Let me see my time. Yes, okay. And that is a single displacement. In a single displacement, you have 2 reactants. One is a compound and one is an element. Same thing for the products. You have 2 products. One is a compound and one is an element. So if you're just counting reactants and products and you're not paying attention to what's there, the double displacement and the single displacement look a lot alike. But if you can just recognize, oh, this one thing, there's only one element there, that's how you're going to distinguish the double displacement from the single displacement. So what happens here is similar to how we have an ionic compound here that switches partners, we're going to have that same thing going on, but instead of it going with another ion, one of the cations is just going to become a pure element, and then the other one that was a pure element is going to become a cation. So let's see how that works. Let's say that I have zinc. I want to do zinc Yes, zinc and copper sulfate. So both of those commonly have a +2 charge. So this would properly be named copper 2 sulfate. Okay. And we are going to react those, and the zinc is going to come in and bump out the other metal. So usually it's 2 metals, sometimes hydrogen's involved. The zinc is going to bump out the copper. So copper is going to be by itself, and zinc is going to be part of the compound. So we'll have copper plus zinc sulfate. Okay, so we call that single displacement because we don't have a second anion for the other metal to get with. So the copper just kind of wanders off by itself, whereas the zinc gets to have a new partner. All right. So on Wednesday, we will talk a little bit about the other way of looking at this, where we pay more attention to what those compounds are. And you can see that we're already starting to pay a little bit of attention to, is it a compound or is it an element? We're going to be a little bit more specific when we talk on Wednesday.